Okay, so let's get started. Let me start with a few announcements. The final exam will be May 7th. I think I said 3 p.m. Central Time. You should let me know as soon as possible if you have a conflict. So far, I've only heard of one conflict, so if it's just one, we'll accommodate that specifically. There's going to be assignment 6 will be assigned on Thursday. And it'll be due on the last Friday of class, which is, I believe, the 1st of May. The exam will cover the whole course. What else? Oh, we'll do review lecture next Tuesday. Next Tuesday is the 28th, I think. And there will be no lecture next Thursday. I have a conflict and I have to cancel the lecture next Thursday. Next Thursday is the 30th. So that means we have one lecture today to finish off Chapter 8. Thursday we'll do a lecture on field theory, continuous version of the Lagrangian. And then next Tuesday a review lecture, and then next Thursday I won't be able to make it. Any questions? Okay. So let me start with a brief summary. We have been using canonical transformations. These are transformations of the canonical variables. Typically we call them lowercase qi and lowercase pi. To a set of new canonical variables, capital Qi and capital Pi. In these transformations, the Hamiltonian goes from h, which depends on Qi, Pi, and t, lowercase, goes to k, which depends on capital Qi, capital Pi, and t. The transformation is canonical if in the transform coordinates the Hamilton's canonical equations are still satisfied. So that means that capital QI dot is given by di K by di capital PI, and PI dot, capital PI dot, is given by minus di K by di capital QI. We can generate a canonical transformation from a function f where f depends on a mix of new and old coordinates. So the new coordinates are the capital Q's and capital P's, whereas the old coordinates are the lowercase q's and the lowercase p's. And there are 4 types of functions f that can be used to generate the transformations. And if we use the transformation equations that are given for a specific type of transformation, then that transformation is guaranteed to be canonical. So early in the chapter, we derived the transformation for the first type. That was when f depended on lowercase q and capital Q. And what we're going to do today is we're going to derive the transformation equations for when capital F depends on lowercase q and capital P, which is the second type. And in the assignment 6, you will derive the equations for the last 2 types, 3 and 4. So we're going to do for type 2 because that will lead eventually to the Hamilton-Jacobi equation. Any questions about this, the general strategy? Okay. So now we'll do the Hamilton-Jacobi equation. If you remember, I motivated this chapter by saying that eventually we'd arrive at a way to describe a system where all the coordinates are cyclic. Remember, if a coordinate is cyclic, then the conjugate momenta, or momentum of that coordinate, is a constant. And so the idea of canonical transformations was to lead us to a methodology that will allow us to make all the coordinates cyclic. So now you've finally learned enough about canonical transformations that we can go ahead and do that. When we go ahead and do that, what we get is called the Hamilton-Jacobi equation. So we'll start by considering a canonical transformation of the second type. So if you remember, the canonical transformation of the second type is given when the function f is f2, and for a second type transformation, the mix of new and old coordinates is to have the lowercase qi's with the capital Pi's and t. And then for things to work out, you have to put in a sum over the number of degrees of freedom of capital Qi and capital Pi. What we need is the total time derivative of f. We're going to need it in a minute, so let's do it now. So it's the total time derivative, so the stuff inside of f that depends on time, we have to take the time derivative of. So df by dt, so let me start with the f2 part. So the qi's depend on t, so if I do df2 by dt, I need to really sum over all the things that f2 depends on. So there's a sum over the degrees of freedom, so then it's di f2 by di qi times dqi by dt, which is qi dot. Alright, then there's going to be a term di f2 by di capital pi capital Pi dot, and there's going to be a di f2 by di t, which I'm going to put at the end. Then the next thing I have here is this sum over capital Qi and Pi. So it's a sum over I equals 1 to n, right? So I'm just going to add it in here. So then I have minus, and then I have to do d by dt of Qi Pi. So that's just the product rule. So I have Qi Pi dot minus Qi dot Pi. And then outside of the sum, I have a di f2 by di t. Alright, so that's just the chain rule applied to f. For the equations of motion to be unchanged by the canonical transformation, ultimately we need the action to be unchanged. Remember, Hamilton's principle tells us that requiring that the action is an extremum, so the time integral of the Lagrangian, gives us the equations of motion. And so this is just like we did in the beginning of the chapter. We said that at most, the new Lagrangian in the capital Q's and capital P's can differ by the old Lagrangian by at most a total time derivative. So we wrote that L, the old Lagrangian, has to be equal to the new Lagrangian plus some total time derivative. So L prime, that's the new Lagrangian. Depends on capital Q's and capital P's. And L is the old Lagrangian, which depends on lowercase q's and p's. Right? If we say the Lagrangian is unchanged by at most the total time derivative, then we know that the action is unchanged, and you'll get the same equations of motion. That's the whole basis of these canonical transformations. So the old Lagrangian, it's easy to go back and forth between the Lagrangian and the Hamiltonian, right? So the old Lagrangian we can write as the sum over the degrees of freedom of Qi dot Pi minus the Hamiltonian. And then the new Lagrangian, L prime, will be the sum from I equals 1 to n. Now it's capital QI dot capital PI, and then it's minus K. Alright, so that's the new Lagrangian L prime. It's just how do you go between the Lagrangian and the Hamiltonian. And of course we need to add in this time derivative, and that's why we calculated it up there. And when you run out of space, well, let's try anyway. So now I put in the df by dt term, so that's going to be the sum from I equals 1 to n. I have di f2 by di lowercase qi dot, plus di f2 by capital PI dot. Still inside the sum, I have minus capital QI PI dot minus capital QI dot capital PI. That's the end of the sum. And then plus di f2 by di t. The first term on the right-hand side of the equal sign, this term here, cancels with the sum from I equals 1 to n of qi dot pi. It's plus, and then over here I have minus the same term. So these two guys cancel. What I'm going to do now, I'm going to factor things in qi dot together, in lowercase qi dot, and then I'm going to factor things in capital PI dot. So let me start by the lowercase qi dots. So on the left-hand side of the equation, I have the sum from I equals 1 to n. So I have a qi dot there, which I'm going to factor out. So I have a PI. And then if I look on the other side of the equation, I have another term here, the di f2 by di qi, that multiplies qi dot. So if I bring it over to the left, it gains a minus sign, and I have di f2 by di qi, and all of that multiplies QI, lowercase qi dot. And on then I have minus h. I'm just going to leave there for now. And then on the other side of the equation, I'm going to do the same thing, but now I'm going to factor out the terms in pi dot. So I have my minus k. I'm just going to leave that there as it is. Then I have the sum from I equals 1 to n. So it's plus. Okay. So the PI dots, I have a di f2 by di capital PI, and then the other term in PI dot, so I have this one, and then I have this one here in green. And then it's minus capital QI, and that all multiplies PI dot. And then I have di f2 by di t at the end. So we impose this to be true, and that will make the transformation canonical. So more specifically, I'm going to impose the two things in parentheses to be equal to 0. So this then gives the transformation equation. So by imposing that first term in parentheses is 0, that tells me that lowercase ti must be equal to di f2 by di lowercase qi. By imposing that the second term in parentheses is 0, I find that capital Qi is given by di f2 by di capital Pi. And so that's the transformations that we needed, right? Because f2 depends on lowercase q and capital P, and so we need to know how to find lowercase p and capital Q. And so we just did the procedure that gave that. And then, as before, the transformed Hamiltonian K is given by the original Hamiltonian plus di f2 by di t. So we derived the transformation equation of the type 2 for canonical transformation. Now, of course, we still don't know how to find f. Right? This is all assuming that we know what f2 is. So the Hamilton-Jacobi equation is going to tell us how to figure out what f2 is. Oops, wait, wrong thing, wrong button. So I have to resize my window here. Okay. So, as a matter of convention, we're going to rename F2. So let S, which is really explicit, S is a function of lowercase qi, capital P, I, and T. Let that be the same thing as F2, which depends on the same thing. Instead of writing F2 everywhere, I'm just going to write S. So that means that the transformation, the equations that we just wrote, lowercase pi is then given by di s by di qi, and the capital Qi is given by di s by di capital Pi. And the new transformed Hamiltonian K is the original Hamiltonian plus di s by di t. It's done nothing. I just replaced F2's with S's. The reason we do that is because we'll see later that S is actually the action. It happens to work out that way. So you want a good choice of S that gives, let's say, a nice Hamiltonian K. All right, so we want a good transformation that's going to make things really easy for us. So a good choice is to make k equal to 0. All right? It's a legitimate choice, right? There must be some value of the transformation S, and when I do the transformed equations, the transformed Hamiltonian is equal to 0. The transformed Hamiltonian k is equal to 0, then all the coordinates are cyclic because none of the coordinates appear in the transformed Hamiltonian. So it actually does have that very nice property. So if k is equal to 0, and we'll figure out how to find S so that that's true, so let's assume that we can. So if k equals 0, then the canonical equation qi dot, which is di k by di capital pi, in that case qi dot would be equal to 0. Similarly, pi dot, capital Pi dot, which would be minus di k by di capital qi, that's also equal to 0. So if qi dot is equal to 0, so dqi by dt is equal to 0, then qi is a constant. All right? So then capital Qi will be equal to constant, and we're going to call that constant beta I. We use Greek letters for constants, that way we know that those things don't change with time for sure. And the capital Pi's we'll call alpha I. Now that's just a common convention. So if we go back to our equation for k up here, if k is equal to 0, then h plus di s by di t is equal to 0. Right? That's what k is. K is equal to h plus di s by di t. So h, to be explicit, is a function of lowercase qi, lowercase pi, and t. Okay. But now, when we work with S, if you remember, is a function of lowercase qi and capital Pi. If we want to work with S, we don't really want to work with lowercase pi. But that's okay, because we know what lowercase pi's are in terms of S. They're di s by di lowercase qi. So every time I have a lowercase pi, I'm just going to write it as di s by di qi. So I have the Hamiltonian h depends on qi. Now instead of saying it depends on lowercase pi, I'm going to say it depends on di s by di lowercase qi, because that's what lowercase pi is, right? And then t. Now what does s depend on? So that's di s by di t. So it's di by di t. And if I put in what s depends on, okay, we just said that. S depends on the lowercase qi. Okay? It depends on lowercase qi. It also depends on capital Pi. The capital Pi's are constants. And we called those constants alpha I. There's one alpha per Pi, right? So let's put in alpha I instead. and then it depends on t. And of course that whole thing is equal to 0. So if we look at this equation, what is this equation? So the Hamiltonian is going to have, potentially like a kinetic and a potential energy term, right? So it's going to have QIs in it, and then it's going to, instead of having PIs, it's going to have di S by di QIs. So it's going to have, something times QIs times something times di S by di QIs. And then the other term is going to have di S by di T's in it. And so ultimately what this is, it's a partial differential equation for S. Right? When you write this out explicitly for a specific system, you're going to end up with a bunch of di S by di variables, in particular di S by di Q's and di S by di T's. So you have an equation that's mixing derivatives of S with respect to different variables. So this is a partial differential equation for S. So if you remember, so far, we've been lucky because all of the math has worked out to be ordinary differential equations. Equations of derivatives of just one variable. But here we're mixing derivatives with respect to multiple variables, in particular Q and T. Before that, we only had total derivatives, and they were only with respect to T. So ultimately, the equations of motion, whether we did it with the Euler-Lagrange equations or the canonical equations of Hamilton, they gave us total time derivatives. And so they were ordinary differential equations. This equation here has partial derivatives of S with respect to multiple variables. So that's a partial differential equation. Partial differential equations are not easy to solve. Ordinary differential equations are easy to integrate, even if they're even easy to do numerically. Maybe there's no analytical solution, but they're very easy to integrate. That's not necessarily true for partial differential equations. So we've mathematically made our life harder. And that's sort of what the promise was. The promise was that we're going to get very simple equations of motion, and they're right there in front of you right now, right? Capital QI is equal to a constant beta I, and capital PI is equal to constant alpha I. And those constants alpha and beta are just given by the initial conditions. So you just put the system in a certain state, and then you measure Q and P, and they stay constant. So that part's easy now. The hard part is, how do you determine what capital Q and capital P are in terms of lowercase q and lowercase p, which are typically labels that you can easily assign. So the trick is to find what's the transformation that goes from lowercase q's and p's to capital Q's and p's. And that transformation is given by this function S, the generating function. And so now the problem is the problem of finding the correct transformation. And the correct transformation is given by this differential equation. This differential equation is called the Hamilton-Jacobi equation. Okay, so I'll just rewrite it out. So this is the Hamilton-Jacobi equation. For some reason I can't write today. This is the Hamilton-Jacobi equation. And it's quite famous. Hopefully you've heard the word before. Okay, so the Hamilton-Jacobi equation is that you write the Hamiltonian in terms of lowercase qi, and instead of lowercase pi's, you use di s by di qi's, where s is a function of the lowercase qi's, the alpha i's, and t. And the Hamiltonian can also depend on t, plus di s by di t, and s of course depends on qi, alpha I, and t, and that's equal to 0. So the alpha i's are constants, and then we have a second set of constants, beta I, and those constants beta I are found by taking di s by di alpha I. So I really don't need to talk about capital Q's and capital P's anymore, because the whole point was the capital Q's and capital P's became constants, and those constants were alpha I and beta I. So that second equation there, beta I is equal to di s by di alpha I, that's just saying that capital Qi was equal to di f2 by di pi. Right, so the alpha was like the p, and the beta is like the q. But we don't really need them anymore because they're constants. So the way to think about this is we have this function s that depends on qi's and alpha i's, where alpha i's are constants. Once you know what s is, you get an additional constant of motion by doing di s by di alpha I, and you'll get beta I. Okay, so that's the way to think of it. But it comes originally from thinking of the alphas and betas as p's and q's. And so now you see why the p was the alpha and the q is the beta. Because the one that comes up in the equation is the alpha, is the one with capital P. And that's because originally we started with a type 2 transformation. So what isn't so difficult in math to get here, but it's a very, very different way to look at the system now. So of course, in many physical systems, it's very difficult to solve that partial differential equation for S. But we'll do an example, as usual, the simple harmonic oscillator, because it's easy. But before that, let's look at this quantity S a little bit better. So far, S is just F2, and I just called it S for convenience. So I didn't really motivate why I should just change the name of it. So let's look at the connection to the Lagrangian and the action. So recall, well, I guess I should point out, when I did the derivation, I just did it here in my head, right, when I did it. There's a mistake in the notes. The mistake in the notes, I think I forgot to copy the K. Let me just write that out as people review the notes later. So I'm missing in the notes. If you compare my handwritten notes with typed out ones, you'll find that they're not consistent. Okay, sorry about that. Okay, so recall the Lagrangian L is a function of qi dot, and t, and then the action S is defined to be the time integral of the Lagrangian. Okay? And it says it has to be a definite interval, say from t0 to t1. And then all of classical mechanics is obtained by requiring that this is an extremum. So let's forget about now, and let's consider the total time derivative of the generating function. Well, I guess I forgot to tell you that the function s up here, which was the generating function, is, we call it, in this context, we call it Hamilton's principal function. Right? That way it's good for it to have a name, since I'm using the same letter S for two different things. So consider the total time derivative of Hamilton's generating function, of Hamilton's principal function. Hamilton's principal function. So I want the total time derivative, ds by dt. So that's d by dt of Hamilton's principal function, which depends on lowercase qi, the constant alpha I, and t. So if I take the time derivative, then I have to do the chain rule, and s depends on the qi's, which themselves depend on t. The alpha i's are constant, so they don't depend on t. If I do ds by dt, I have to do the sum over the number of degrees of freedom. Then I have di s by di qi dot. I don't get anything from the alpha term, and then outside of the sum, I have di s by di t. Now, the transformation equations they give me that di s by di, or the transformation equations are that lowercase pi is di s by di qi, right? That's for a type 2 canonical transformation. So that term in the sum there, the sum over I from 1 to n is the pi times qi dot. And then the Hamiltonian, or the transformed Hamiltonian k, is equal to h plus di s by di t. So remember, we chose s so that k was equal to 0. So what we really have is that h, the Hamiltonian, is minus di s by di t. Right? If I put that in here, I get the sum from I equals 1 to n. Instead of di s by di qi, I'll write that as pi. That's pi qi dot. And then instead of di s by di t, I'll write that as minus h. And hopefully that looks familiar because we just used it earlier. Alright, so that's equal to L. I use the transformation equation in that step there. So what we find is ds by dt, so the total time derivative of Hamilton's principal function, is equal to the Lagrangian. So Hamilton's principal function, f, is equal to the integral over time of the Lagrangian, and then plus some constant. And so now you can see why we called it f, because Hamilton's principal function is related to the integral of the Lagrangian over time, which is the action, plus some constant. And of course that constant doesn't change the equations of motion. So this thing, excuse me, this thing here is the action. So Hamilton's principal function, f, is equal to the action within an additive constant. That should surprise you a little bit. It's kind of weird, right? We did kind of a full come around back to the beginning. We went on this crazy tangent of Hamiltonians and canonical transformation, completely arbitrary variables, capital Q's and P's to describe a system. And then we had this framework of the generating function to find these canonical transformations. And then when we choose a specific case of a canonical transformation that gives us a zero Hamiltonian, it turns out that the function that generates that canonical transformation is the action. So that's pretty neat. So there's some deep meaning to this action. And there better be some deep meaning to it, because all of classical mechanics is obtained by requiring that the action is stationary. Alright. So that's pretty remarkable, I think, and pretty weird. So now let's consider a special case. So consider the case where the Hamiltonian is constant. So the Hamilton-Jacobi equation, which we write as H of Qi di S by di Qi T plus di S by di T equals 0. So that's in general the Hamilton-Jacobi equation, right? That's the general case. If H is constant, say H is equal to some constant E for the total energy, usually what H is when it's constant. If H is constant, then we can separate the time dependence out of S. So remember, just because H is constant doesn't mean that S is constant. So the problem with these partial differential equations, here you have di-s by di-q's mixed in with di-s by di-t's. The problem is you can't integrate them straightforwardly because you have both q's and t's, and q depends on t. So it's not trivial to integrate. However, one of the techniques of solving these partial differential equations is if you can factor out the time dependence into different functions. So what we do is we say that, let's try the solution when s, which normally would depend on qi, alpha I, and t. Let's try the solution where s depends on a function w that only depends on qi and alpha I. And then we'll add a term minus e times t. In that case, I can rewrite the Hamilton-Jacobi equation as Hamiltonian. So the Hamiltonian in the Hamilton-Jacobi equation, you have it depends on qi, and then it depends on di-s by di-qi. But if I say that s can be written in terms of these two different functions, the di-s by di-qi part is only in the w. So then I have di-w by di-qi. And then h doesn't depend on t. And that plus di-s by di-t equals 0. If I look at what I imposed of the solution for s, if I do di-s by di-t, I get minus e. So I'll just move that to the other side of the equation. And so this is a more simple version of the Hamilton-Jacobi equation when the Hamiltonian doesn't depend explicitly on time. So this maybe looks a little bit familiar. H, some function equals E. Like some of you have a class after this, right? It's called quantum mechanics. Quantum mechanics, you have H, the operator for H, times something, maybe the wave function, equals E times the wave function. It's actually very similar already to the time-independent Schrödinger equation. And we'll see that it actually is the time-independent Schrödinger equation in classical mechanics. So this W basically tells us everything, right? So this W is called Hamilton's characteristic function. So you have Hamilton's principal function S and Hamilton's characteristic function W. Alright, so this is all very abstract. How does this actually give us a partial differential equation for anything in the real system? So let's do an example of following this. This is example 8.5. And it's the simple harmonic oscillator with the Hamilton-Jacobi equation. So we start with the Hamiltonian. So for a simple harmonic oscillator, the Hamiltonian is p squared over 2m plus k over 2 q squared. Right? If you want to think of it's a simple harmonic oscillator, right? So you only have one degree of freedom, usually you call x, So Q is like X, and then P is like the momentum at X. Right? And then we saw that in phase space, this draws an ellipse. So we write this using Hamilton's principal function. S. Okay, so remember, so the Hamilton-Jacobi equation, so the HJ equation is that H, the Hamiltonian, which depends on Q. I'm not going to put any QI's in here because there's only one, right? So H depends on Q, it depends on di S by di Q, that's lowercase p, and T plus di S by di T equal to 0. Right? That's the Hamilton-Jacobi equation. And I know H. So remember, di S by di Q is our way of writing lowercase p in the Hamilton-Jacobi formula. If I write the Hamilton-Jacobi equation now with this specific Hamiltonian, I have the first term of the so it's the Hamiltonian plus di S by di T. So I have to write the Hamiltonian in terms of Q and di S by di Q. So the first term in the Hamiltonian is p squared over 2m. So that's 1 over 2m, and then p we call di S by di Q. Second term stays unchanged, so it's k over 2 q squared. And now to have the Hamilton-Jacobi equation, then I have to have this last term plus di S by di T equals to 0. So that's the procedure. You need to know what the Hamiltonian is, and then you put it in to the Hamilton-Jacobi equation where you've written the Hamiltonian in terms of di S by di Q. So you've removed all the p's in favor of the partial derivatives in Hamilton's principal function. And so that's it, right? That's Hamilton-Jacobi equation for simple harmonic oscillator. So this is a partial differential equation for S. And so now it's a matter of mathematics to solve it. So in this case, since H does not depend on time, we try separation of variables. That's the mathematical name of the method. So let's try a solution where we write our function S. Oops, I said I wouldn't put any I's in there. So our function S depends on Q, some constant alpha, which we haven't determined yet, and T. Let's try writing that as Hamilton's characteristic function of W of Q and alpha, and then minus, let's say, alpha T. Okay? So I'm going to try this as a solution. It's a little bit arbitrary that I chose the same alpha to go with the T as the alpha that's inside the W. But I'm going to try this solution and see what happens. So if I put that into the Hamilton-Jacobi equation, then I get the first term 1 over 2m. Now di S by di Q, the only part of S that depends on Q is W. So I have di W by di Q all squared plus k over 2 q squared. And then di-s by di-t, only the minus alpha t term has a t in it. And so di by dt of that is minus alpha, and let's move that to the other side, and so the whole thing is equal to alpha. So that's actually good, because on the left-hand side I have only w's and q's, and w only depends on q, because alpha is a constant. And then on the right-hand side I only have alpha. So I can write this, now it really doesn't matter, I can say this is the total derivative dw by dq squared plus k over 2 q squared equals alpha. Right? Let's go back one line and think about alpha. So 1 over 2m dw by dq is p, right? So what I have on the left-hand side is 1 over 2m p squared plus k over 2 q squared equals my constant alpha. So note that that's actually equal to the total energy, right? Because that is the total Hamiltonian. So alpha is the total energy. So the separation of the variables that we did is really the same one that I introduced earlier as a possibility, that you use the energy. And so it actually works. It is alpha is the energy. So now that it's a total differential, it's not a partial differential equation anymore, it's an ordinary differential equation. And it's a particularly easy one. So I can write this as dw by dq is going to be equal, so I have alpha minus k over 2 q squared then I multiply all of that by 2m and take the square root. If I introduce omega equals to, I think, the square root of k over m, then I can rewrite this as dw. So I'm going to put in this omega here, and you can work out the math by yourselves, it's easy. But I'm going to get rid of the k's in terms of omegas, because it simplifies it a little bit. And then what I'm going to do is I'm going to move the dq to the other side and put an integral sign. Okay, since I know the total derivative of dw by dq, then it's easy to write that as an integral. So dw is now equal to the integral, and then the square rooty thing, where I've replaced the k's with omega. So when you do that, you get 2m alpha minus m squared omega squared q squared. That's all underneath the square root. And then it's integrated over d2. Oops, and that's, if I put the integral sign, I take the d out of the w. Okay? And so that's something that you can integrate, right? And in particular, now that we found Hamilton's characteristic function w, you can find Hamilton's principal function s. Remember, s was w minus alpha t. So it's minus alpha t plus w. which is this integral. So we know what alpha is, right? Alpha is the total energy. So it's not something that we need to understand and to figure out. We can just measure it easily. Right, we just take the system at a given time, put in what we have for P and Q, and then we get what the Hamiltonian is, and that's the total energy. So the other constant that we need, because remember there's another constant of motion, beta. So another constant of motion, beta, is given by, but remember the beta is like the capital QI, right? So the beta was given by di S by di alpha, where alpha was like the capital Q. I think I did the other way around. Beta is like the capital Q, and alpha is like the capital P. And the generating function S of the canonical transformation depend on lowercase q and uppercase p. So let me do di S by di alpha. So I have S above there in terms of an integral, right? So di S by di alpha, well the first term, if I take the derivative with respect to alpha, is just t. And then the second term, I think, is wrong in the notes. If I take the derivatives, I can move the di by di alpha inside of the integral, right? So I have to do the integral of the square root. So the integral of the derivative of the square root. So I'm going to use the integral for now. So the derivative of the square root is 1 over half of the square root, and 1 over 2 times the square root. So I'm going to have a 2, and the square root is 2m alpha minus m squared omega squared q squared. And that's all dq. But now it's di by di alpha of that square root, right? So I have to do a chain rule. So I have to do a derivative of the inside of the square root with respect to alpha. And the derivative of the inside of the square root with respect to alpha is 2m. So that's where I think there's a mistake in the notes. I forgot to put the 2 in the notes that goes in the denominator. Because when you do the derivative of the square root, you have a half of the square root, right? So I believe that 2 should actually cancel. Oops. So now you're left with this integral of m over the square root of a constant over the square root of some constant minus some other constant times q squared. That's something you can look up. And if you look it up, you can find that that integral is actually equal to 1 over omega times inverse sine of q times the square root of m omega squared over 2 alpha. Simple as that. So that's our constant beta. Alright, so that's just an integral, right? This integral is like the integral of some constant a, some constant b, minus some constant c, q squared, dq. So it's not such a terrible integral to look up. In fact, it's not so hard to solve, I think, with trig functions. But that's math, we don't care so much. Okay, so this gives us beta equals minus t, and now something with q in it. ideally we'd like to know what the equations of motion are. So it'd be good to know what Q is in terms of beta, not beta in terms of Q. Because Q is a function of time, and beta is a constant. So I can invert this, right? So if I move, this becomes beta. If I move the t to the other side, I get beta plus t. If I multiply all that by omega, then I get omega times beta plus t is inverse sine of Q times the square root of m omega squared 2 alpha. And so now I can take the sine of all of this, so that sine of inverse sine is nothing. And if you invert this and then multiply the thing that multiplies the Q, ultimately you get that Q of t is equal to the thing that was multiplying the Q, but 1 over that. So 2 alpha over m omega squared times sine of omega times beta plus t. So it does eventually give you the solution. So it's a little bit mathematically, clearly not the easiest way to solve the simple harmonic oscillator, but it's quite powerful, especially in its insight. So we're not quite done, right? In the Hamiltonian formalism, we should also specify how the momentum changes with time. So the momentum P is di S by di Q from the transformation equation. Right. That's how we started the whole thing in the beginning. We replaced P's with di S by di Q. So that's equal to di by di Q of S, and S is that annoying integral. So it's minus alpha t plus the integral of the square root of 2n alpha minus m squared omega squared q squared dq. The fact that there's an integral there is not so annoying because now we're going to take the derivative with respect to q. And since everything is constant in that square root, whether I do partial derivative with respect to q is the same as if I do total derivative with respect to q. So if I do derivative with respect to q and then integrate with respect to q, it's like not doing anything. So that actually works out pretty easily. The first term minus alpha t doesn't depend on q, and when I do di by di q of the integral of something, integrated over q, I just get something. So I just get the square root of 2m alpha minus omega squared m squared q squared. So rewrite that again on the other page. So I found that p was equal to that square root, which is the square root of 2m alpha minus m squared omega squared q squared. Let me sub in now the fact that q, so let me write q squared. From the solution that we had, q squared was 2 alpha over m omega squared, and then it will be sine squared times the omega of beta plus t. If I sub that in, I can factor out a square root of 2m alpha. Then I'm left with the square root of 1 minus sine squared of the omega times beta plus t. And if I take 1 minus sine squared, that's cos squared. So for p, and then cos squared square root it, this gives me cos of omega times beta plus p. So a rather painful way to find p and q. But now we did achieve the original goal, which was to make all the variables cyclic. But then the whole problem is then to solve the partial differential equation. Any questions about that? Okay, so the next section in the notes is on action angle variables. And that's similar. It pushes the formalism of the Hamilton-Jacobi equation much further. And you should read that section. What it allows you to do is when you have a system that has some periodic motion in it, you can find the frequencies associated with those periodic motions without actually having to solve the equations of motion. So it's quite useful. It's particularly useful in systems that are related to quantum mechanics, because often in quantum mechanics you need to know frequencies of things. Now, if you think of the very simple Bohr atom, the Bohr model of the atom, the energy of the photons that are emitted when an electron jumps from one level to the other is h times the frequency. So the h times the frequency of the photon is the change in energy between the states and the different orbits in the Bohr atom. So in quantum mechanics, there's a deep relationship between frequencies and energy. And so this action angle variable is a formal way to do that in classical mechanics. And in the early 20th century, when they were trying to go to quantum mechanics smoothly from classical mechanics, the first way that they found to do that was through these action angle variables. The Bohr atom is one of the ways where it works very nicely. Except the ground state energy was wrong, but they just ignored it. But for a while, they looked for how do you go from classical mechanics to quantum mechanics, because quantum mechanics was sort of discovered independently, not as an extension of classical mechanics, but rather as a set of rules that the world appears to follow. And then they tried to reconcile the two, and then this action angle variable was one way that they could do that. That's called the Sommerfeld-Wilson prescription from classical mechanics. It's the old school classical mechanics to quantum mechanics prescription. Okay, so I do encourage you to read about it, but the material is maybe a little bit advanced for an undergrad course. But I will point out that the Hamilton-Jacobi equation is regularly covered in undergrad. You guys are probably freaking out because it's so complicated. So when I want to finish up this chapter, I want to talk a little bit more about this connection to quantum mechanics. Because I know some of you are taking quantum mechanics, and some of you probably will take it in the future. So I want to look at the connection to quantum mechanics. So, to make the connection to quantum mechanics, I have to assume a little bit of knowledge of quantum mechanics, because otherwise, clearly you can't see the connection. So, let me just recall a few key points. Some key points from quantum mechanics. Let's do all of quantum mechanics in 4 bullet points. In quantum mechanics, the state of a system is given or defined or completely described by a wave function. And sometimes we write that wave function with these funny symbols around it, and we call it psi. So psi is the wave function. So you can think in classical mechanics, you describe a system by specifying all of the q's and all of the p's. In quantum mechanics, you have to specify this function psi. In quantum mechanics, you have these things called observables. And observables are obtained by operating on the wave function. So for example, if you want to know let's say the wave function is describing an electron, and you want to know the position of that electron. The way you do that is you need an operator, which is a mathematical object. So let's say it's the operator that tells us the x position of the system. Well, that operator, you multiply it by the state function, and then what you get is like an eigenvalue equation. You get the thing that you're trying to measure, x, times the wave function. So in quantum mechanics, if you want to know something about the system, you have to operate on the system. And when you operate on the system, you apply a mathematical expression, whatever, it'll give you the value that you're trying to find. So each value you're trying to measure has associated with it an operator. Okay. Operators, in general, don't commute. So typically, if I want to measure x and then y, that's not going to be, I'm not going to get the same values as if I measure y and then I measure x. So in general, they don't commute, but sometimes they do commute. In fact, there's very specific rules about which operators commute and which don't. So x and y, if they were really positioned, x position and y position, they actually commute. But if x and y were x momentum and x position, then they don't commute. And so generally, the things that don't commute are the things that have Heisenberg uncertainty principles. There's sort of 2 ways to do quantum mechanics, right? So in the Heisenberg representation, the state vector, psi, so psi describes the system in quantum mechanics. We use a slightly different word if we're doing the Heisenberg way of quantum mechanics or the Schrödinger way. So the Heisenberg way, we call psi the state vector. And in the Schrödinger way, we call psi the wave function. So they're an entity that's representing the same thing, basically. So in the Heisenberg representation, the state vector is constant, and the operators are time dependent. let's say I have an electron moving along the x-axis. In the Heisenberg representation, that thing that is the electron is described by a constant thing called the state vector. To know where it is as a function of time, I have to use this position operator, and that position operator depends explicitly on time. So when I put in different values of time, and I do x, when I take the operator x and I act on psi, I get different values at different times because x is different at different times, the operator. Okay? The other way of doing quantum mechanics in the time-dependent Schrödinger in the time-dependent Schrödinger representation, the wave function depends on time. And the operators are constant. So in the Schrödinger representation, I have an operator that tells me the position of the system, and that operator is the same no matter what time it is. However, the wave function that describes the system changes with time. And so the Schrödinger equation tells you how that wave function changes with time. Whereas in the Heisenberg representation, you want to know how the operators change with time. Okay, so that was quantum mechanics in 10 minutes. So now I'll do a few connections with the thing that we've done so far. So I want to look at two things. So I want to look at Poisson brackets and the commutators. So Poisson brackets, as you recall, that's a thing from classical mechanics. And commutators is a thing of quantum mechanics. And the two are related. So I obviously don't have time to do a quantum mechanics course now. But hopefully what you've studied is some of the properties of the commutators of these operators. And just like we did with Poisson brackets, we found that clever Poisson brackets with the Hamiltonian tell you how a system evolves with time. Clever commutators between operators in quantum mechanics also tell you how the system evolves with time. So the prescription to go from classical mechanics to quantum mechanics is that you start with classical mechanics. We have Poisson brackets of functions of the canonical variables. So you take all your equations of classical mechanics that are written with Poisson brackets, and that's why the Poisson brackets are so important. Every time you have a Poisson bracket, you replace it by 1 over IH bar commutator of U and V. So you can write any classical mechanics equation in terms of Poisson brackets, and you'll get the classical mechanics version by replacing the Poisson brackets with 1 over IH bar commutator of the same thing. So recall how a function of the canonical variables variables changes with time. In classical mechanics. In classical mechanics, we could find that if you do df by dt, you could find that simply by taking the Poisson bracket of f with the Hamiltonian, and then if f depended explicitly on time, you'd have to add in a df by dt. Let's say f is a function of position. I can find how that operator f, the equivalent operator f, changes in quantum mechanics simply by doing so I put hats on things. So I have, instead of df by dt, I have df hat by dt. So how the f operator changes with time. I need to replace Poisson brackets with 1 over IH bar commutator. So then it's going to be the commutator of f with the Hamiltonian operator. And then it's plus df by dt. This is precisely the Heisenberg equation that you get for how operators change with time in quantum mechanics. Just in case you didn't know, h bar is Planck's constant h over 2 pi. So that's one. Now I'm going to do a little bit more, not as obvious. So that was Poisson brackets and commutator. There's actually a deep connection between the Hamilton-Jacobi equation and the Schrödinger equation. The Hamilton-Jacobi equation and the Schrödinger equation. Turns out the Hamilton-Jacobi equation is the classical mechanics version of the Schrödinger equation. So now if you haven't done any quantum mechanics, then you're going to be lost. But maybe you can follow a little bit. So recall the time-dependent Schrödinger equation. You can write the time-dependent Schrödinger equation as h of qi, pi, and t, so some operator, times the wave function, and that's equal to I h bar psi by dt. Now, that's not quite the right way to write something in quantum mechanics, because I need operators for things. In particular, the operator for momentum in quantum mechanics, right? So we're still in quantum mechanics. The operator for momentum is given by h bar over I di by di qi. So think of, for example, the qi could be x, right? So the momentum operator, px, is h bar over I di by di px. Di by di x, sorry. Right? So consider a solution to the time-dependent Schrödinger equation of the form psi is given by some amplitude times e to the I over h bar, and then some function s, which I'm going to say depends on q, I, and t. This is what we call a plane wave solution. Alright, so there's lots of problems in quantum mechanics where a possible solution to the time-dependent Schrödinger equation is a plane wave solution. So, in a plane wave solution, if I want to know pi psi, so I want to know the momentum operator on psi, then I have to do h bar over I times di psi by di qi. And I'm interested in knowing pi psi because the time-dependent Schrödinger equation up here with h has a pi psi in it. So if I do di psi by di qi, given that specific plane wave solution, you get h bar times psi, because it's an exponential, right? And then it multiplies di s by di qi because of the chain rule. And the other thing I need in the Schrödinger equation is the right-hand side, the di psi by di t, or I h bar times that. The other thing I need is I h bar times di psi, oh I keep trying to do W, di psi by di t. So I do I h bar times di psi by di t given this plane wave solution. Because it's an exponential, I get the original thing, so I have minus h bar, that comes out of the what's in front there. I have the original solution, and then I have, because of the chain rule, di s by di t. So now I put this into the Schrödinger, the time-dependent Schrödinger equation. I'm going to write my Hamiltonian. It's Qi. The Pi part is h bar psi times di s by di qi. So I'm going to put the di s by di qi in here. And that's this thing. And then the h bar psi I'm going to keep outside. Then the other term I have is on the right-hand side, I have this IH bar di psi by di t, which I said was minus h bar psi times di s by di t. So I bring that also to the left-hand side and factor out the h bar psi, and it's a plus di s by di t. And that all multiplies h bar psi, monoway now, and is equal to 0. All right. So this psi cannot vanish. Of course, if psi is equal to 0, then you can't say anything. But that's generally not the solution you're interested in. So if psi is not equal to 0, then the thing in brackets is equal to 0. So then h of qi di s by di qi t plus di s by IT is equal to 0. So I haven't done any classical mechanics, that was all quantum mechanics. But this equation that I got is awfully familiar. Where is it? Well, obviously you understand where I'm going with this. I get exactly the Hamilton-Jacobi equation for S. So in quantum mechanics, and QM, sorry, the Hamilton-Jacobi equation gives the equation for the phase of plane wave solutions. That's a little bit complicated thing to say. For quantum mechanics, the Hamilton-Jacobi equation gives the equation for the phase of the plane wave solution. So what we did is we took the Schrödinger equation, we assumed a solution of the form a plane wave solution with this exponential times I over h bar s. The s part, we call that the phase of the wave. And that phase, the equation for finding that phase, is the Hamilton-Jacobi equation. And then we also know that this phase S, at least in classical mechanics, is the action. And it turns out the action also appears in quantum mechanics. And when you move to quantum field theory, it's again, everything is based on the action. These last little tidbits on quantum mechanics are obviously not part of the exam, but hopefully they're a little bit interesting, especially if you're taking quantum mechanics. Okay? Any questions about that? Okay, so Thursday we'll have a lecture on the classical field theory, and then next Tuesday we'll have a review. If there's no more questions, that's it for today. Thanks everyone.